Hey students, welcome back to another section on chemistry. This is going to be a little bit longer than our previous ones on chapter 4. We're going to be talking about sections 4.3 today. And so 4.3, we're going to talk about how we distinguish from one atom to the other. Just as apples may come in several varieties, or even Pop-Tart flavors or soda flavors or coffee flavors, they all come in different sizes and varieties. So how do you call these different varieties? What do we call those? Well, we'll call those in chemistry, we'll call those isotopes. We'll talk about those, but difference between apples. They're all apples. They're all part of the same apple family, but they're different. They're different, okay? So how do we distinguish from one from the other? That is called the atomic number. The atomic number, I like to say it, is the identifying character trait of an atom. So like a birthmark or a scar that you might have, that is always going to be with you, or your dental records. That's many times how they might unfortunately have to identify a body, a dead body, and so it's an identifying character trait. Your dental work, a scar. I have a scar on my hand here, or if you have a birthmark that may mark you, that you have that for the rest of your life, unless you get removed, similar to a tattoo. So the atomic number is that identifying character trait. So they're made up of different number of protons. So what makes one atom different from another is the number of protons it has, and that's called the atomic number. Okay. And we actually refer to elements by their atomic number. So element number 1 is hydrogen. Now, element number 3 is lithium. So that not only tells me its number, but it tells me its number of protons. So here's an example of that. Hydrogen has an atomic number of 1 because it has 1 proton. It also has no neutrons. Let's skip down to lithium. I mentioned lithium, symbol Li, has atomic number of 3 because it has 3 protons. We'll call lithium element number 3. Jump down to say carbon, a very common one. Its symbol is C, and the atomic number 6, and it has 6 protons. So these, you're noticing that the protons determine the atomic number. They're the same thing. Okay, so now the neutrons will change. Okay, the neutrons will change, but the protons will always remain the same. So any element that has 4 protons has to be beryllium. Any element that has 7 protons has to be nitrogen. So here's an example of nitrogen. The element nitrogen is shown here in liquid form, has atomic number 7. So how many protons and electrons are in a neutral atom? Now, I told you last time that protons are positive, and that this is a neutral atom, means it has no charge. So if you have 7 positively charged particles in the nucleus, for it to be neutral, you have to have an equivalent 7 negative. So if you have 7 positive, you have to balance those out with 7 negative. So not only does the atomic number tell us the number of protons, it also tells us the number of electrons. So nitrogen has 7 protons and 7 electrons if it is neutral. Now, later on in this year, when we talk about bonding, we're going to talk about ions and when something will form an ion and it'll lose or gain an electron. So we'll have positively charged atoms. We'll talk about those later. But for now, all the atoms we talk about on this periodic table I'm introducing you to are going to be neutral, meaning they have no charge, which means protons equals electrons. Okay, so the atomic number of a given proton, which is neutral atom, equals the number of protons. So therefore, must have 7. 7 protons, 7 electrons. Okay, so we'll just go through a couple of these right here, completing this table. You have potassium, element number 19. That means it's going to have 19 protons. Okay, what element is going to have 5 electrons? Well, we'd have to look at our periodic table. That if it has 5 electrons, I mean that's 5 protons. If it has 5 protons, it has an atomic number of 5. Element number 5 on our periodic table is boron. Okay, element S, which is sulfur, has 16, atomic number 16. Therefore, it's going to have 16 protons and 16 neutrons. Okay, so that's just kind of give you a little introduction to atomic number. Now we're going to talk about the mass number. The mass number is the number of protons plus the number of neutrons. Okay, so we know the number of protons from the atomic number. The number of neutrons is protons, is going to be the mass number minus protons here. Okay, so number of neutrons is the mass number minus the atomic number. Okay, so let's look at gold here. Gold is this element Au. And so we have an atomic number of 79 and an atomic mass of 197. So the mass is the bigger number. Mass is usually the bigger number. Actually, it's always the bigger number. Its mass is 197, and the atomic number, the number of protons, is 79. So this 179 is protons plus neutrons, and this 197 is protons plus neutrons, and 79 is just the number of protons. So if we were to figure this out, how many neutrons we would have, we have to subtract 197 minus 79. That'll give us the neutrons. So let's look at another example. How many protons, electrons, and neutrons are in each atom? So beryllium has an atomic number of 4 and a mass number of 9. So we'll take the atomic number and we subtract 9 from 4. That tells me how many neutrons are 5. So it has 4 protons and 4 electrons based on this. And it has 5 neutrons based on 9 minus 4. Let's try another one. Neon has an atomic number of 10 and a mass number of 20. The atomic number tells me protons, which also tells me electrons. So that means it has 10 each of protons and 10 electrons. If I 20 subtracted from 10 will give me that it has 10 neutrons. So neon has 10 protons, 10 electrons, and 10 neutrons. Lastly, sodium has an atomic number of 11. So that means it has 11 protons and 11 electrons. Now to find the number of neutrons, I take the mass number, 23, minus 11, that is 12. It has 12 neutrons. Okay, so those are some quick ways to do that. There's the math on that, how we figure that out. The number of electrons is the atomic number, and the number of protons is also the atomic number, and the number of neutrons is the mass number. The larger number, you subtract the smaller number. That'll give you the number of neutrons. All right, so just a couple of problems here that you'll see. I gave you some homework in there, and I want you to look at some isotopes with me. Let's talk about isotopes. And isotopes mean, iso means same, and tope means place. It means it lives at the same place on the periodic table. But just like a Gala apple and a Red Delicious apple are both apples, they are different from one another. So you can have isotopes of an element that have different number of neutrons, but they have the same number of protons. So here's an example of that, neon. Neon, all of these are neon. Why are they all neon? Because they have 10 protons. Any element that has 10 protons is neon by definition. Okay, but you can have in the nucleus, so we have 10 electrons, 10 protons because it's neutral, 10 protons, 10 electrons, 10 protons, 10 electrons. What can change is the number of neutrons. Notice the neutrons here are 10. Neutrons in this middle one are 11, and the neutrons here are 12. These are all neon because they all have 10 protons. But they're isotopes, or you think of them, they might be brothers and sisters in the same family, just different forms, or different types of apples, or different types of oranges, or different types of flowers, okay, that are maybe in the daisy family, right? So this is going to have a higher, the mass of this is going to be 10 protons plus neutrons is the mass. So this is neon 20 because 10 protons plus 10 neutrons. Remember, we only use protons plus neutrons to equal the mass. Here, the mass is still going to be neon, but this is neon 21 because 10 plus 11 is 21. Likewise, 10 plus 12 is neon 22. So the most frequent or the most abundant neon in our universe is neon 20, but there are other forms in smaller percentages of neon 21, neon 22. All right, so there are other isotopes of carbon, carbon 12 and carbon 13. Carbon 14 you might have heard in carbon dating. So there are isotopes almost for every element there are out there, okay? So what I want to do is how you calculate the atomic mass. Okay, how would you actually calculate? How do scientists come up with that? So what you do, you compare the relative masses to a standard isotope of carbon 12. So carbon 12 is the standard reference for an isotope. It has a mass of exactly 12 atomic mass units. That's called AMU. An atomic mass unit is what everything is based off of. Okay, so it's when we remember when we studied standards, I told you that what the meter is based off of and what the speed of light is based off the speed of light, and that the time is based off a cesium atom, how it might give off a certain type of radiation, a certain frequency. That's what time is based off of. And so other ones are based off, say, Planck's constant as well. So all these are based off a constant. So you can think of this as the standard for atomic mass is carbon 12. It was called an AMU, atomic mass unit. So for instance, let's look at a simpler one here. Let's look at hydrogen. Hydrogen, 99.985% of all the hydrogen in the universe is made of hydrogen 1, meaning it has an atomic mass of 1. It has 1 proton and 1 neutron. Okay, so I'm sorry, 1 proton and no neutron. So it has an atomic mass of 1. 0.051%, excuse me, 0.015% of the universe is made up of this type of hydrogen, hydrogen 2, meaning it has 1 proton and 1 neutron with an atomic mass of 2. And then there's actually atomic mass, what's called tritium, which is called heavy hydrogen here, which makes up heavy water. And that is very, very small percentage. So what we do, you take a weighted average of all of these, 99% of made of this mass, 0.015 made of this mass, and negligible to this mass, and you add those up, just like you might add up your grades. Quizzes in your class are worth 40%, you add that up and multiply it times 40%. If the tests are 50%, you add that up, multiply times 50. And the remaining 10% is your class participation. You average that up, multiply times 0.1. So the 40, 50, and 10 are the percentages, and so it's a weighted average. So another version of this is carbon 12. 98.89% of carbon in the universe is made of carbon 12. But another 1.11%, not an insignificant amount, but not a lot, is made up of carbon 13. So when you average, you take the weighted average where 99% is 12 and 1.11% is 13. The average, the weighted average is 12.011. So we'll do one of these in class together. I just wanted to give you an understanding that. So the atomic mass is a weighted average of all the atoms naturally occurring for that element, okay? So a weighted mass of chlorine, how you would do that here, the total number of protons in chlorine is going to be, total number of protons is 17. Okay, so it's going to be 17 plus 17 plus 17 plus 17. These are 17 in each one of these. See that? 17 in here, 17 in here, 17 in here. So we add those up. 17 plus 17 is 68. And then you add the total number of neutrons up. So that would be 18. 18 plus 18 plus 20. That's going to give you 74. And you divide that by the total number of different isotopes. You have 4 different isotopes here. So this is the sum of the protons, sum of the neutrons between all of these isotopes. You divide it by the total number of isotopes, 4, and that's where you get the average atomic mass of chlorine is 35.5. Okay, so that's how we understand relative abundance. We're going to do a lab together next time together. I do want to do a quick introduction with you for the periodic table. We're going to be using the periodic table starting next class. And so why is it useful? What is the periodic table? I'm going to give you, there's a whole chapter on the periodic table. Just give you a little introduction now. It's easy to compare one property to the element. So it is an arrangement of elements that are separated into groups based on repeating properties of that element. Okay, they're related to groups, are also called families. Okay, so here's the periodic table. This is an older version. We'll be working with a much newer, more interactive version in class together. And so each horizontal row is what's called given a period, meaning that they, as you move across, they act similar to one another as you go across. So here's what a period is. It's a row. So this would be period number 4, because it's number 4 here. So potassium, calcium, vanadium, chromium, manganese, iron, cobalt, nickel, all of these are all trying to achieve the same goal. They're trying to be like this last one on the period, chromium. Okay, I'm sorry, krypton. Krypton, Kr is krypton. All right. Row number 5, period number 5, rubidium, strontium, molybdenum, uh, silver, indium, iodine are all trying to achieve the same goal, to be like xenon. We'll talk about that later, but in general, they're trying to arrange their electrons to look like the last one in a row. So you can think of periods as they all have the same goal in mind, to be like the last one in their row or period. Okay. Differently, a group or family, they act similar to one another. They have similar chemical and physical properties, much like a team will act similar. So whether it's a basketball team or a volleyball team or a chess group, or maybe you're a group that loves to play Minecraft or whatever it is, you're going to have different skill sets that are similar to one another. Some maybe have different levels of the skills, maybe some may specialize in different things, but you're going to act similar. So when you go to the dojo, you're going to know how to act in one way versus when you go to the gym to work out, or you might go to the basketball court, you might go to chess club. Okay, so groups are the horizontal. So beryllium, magnesium, calcium, all of these in this group right here are in group 2, and some periodic tables, older ones may call this 2A. We're going to call them both. So they'll act similar to one another. In group 1, hydrogen, lithium, sodium, potassium, and all those down there will act similar to each other in a chemical reaction. Okay, similar. That's a group 7. This is also group 17. Fluorine, chlorine, bromine, iodine will act similar to one another. So for right now, just know that they're based. The periodic table is based on groups, how they act similar to one another in a chemical reaction, and then they will be in periods that they're all trying. In there, they're always trying to achieve the same goal, which is to be like the one last in their row or period. So that's just a little introduction to the periodic table for now. We'll get into this in more detail in the coming weeks. Talk to you soon.